So here is the explanation of the power factor condition on the motor of synchronous motor. So at unity power factor, this one happen when the field current is sufficient enough. Means that the field current that induced to the IF to the field to excite the poles on the rotor enough to produce the air gap flux and as demanded by the constant supply voltage. Then the magnetizing current and or reactive lagging reactive VA required from the AC source is 0. So the Q is 0. And the motor operates at unity power factor. Means that P equal to P only lah. It's not P plus Q lah. The field current which causes this unity power factor called normal excitation or normal field current. So we have a normal excitation condition. But when at lagging power factor, means that the Q is absorbed from the source. The field current is not sufficient enough to produce the required air gap flux as demanded by V and by the source voltage, phase voltage. So we need additional magnetizing current from the AC source. So it's import from the source the additional magnetizing current. So this magnetizing current produce diffusion flux. Means that the constant flux set up by the DC supply rotor winding. So the motor said to be operated under lagging power factor or under excited condition. And the field current is not enough to produce the air gap flux, so it import from the line. So it operates now as a under excited condition. So the power factor will be lagging. So it behaves like inductor, absorb Q from the line. In case 3, whereby the condition to be a leading power factor on the right hand side portion. So if the field current is more than the required field required by the motor to produce the flux, so this excess field current produces excess flux, and the flux set up by the DC supply rotor which result the air gap flux must be neutralized by the armature winding. So the armature winding will draw leading VA and VA here, or it supply and it will supply the Q to the line. The magnetizing current leading voltage by almost 90 degrees from the AC source. So now it operates under leading power factor. So you can see here over excited, under excited, and normal excitation. So what happens when the load changes? And this one, what happens when we change the IF here? We control the field intensity, field current intensity. So the behavior will change from under excited unity power factor and or over excitation. What happens when we change the load to the motor, synchronous motor? When the load is which attached to the shaft of the synchronous motor, we attach the motor with the load. The motor will develop enough torque, and whereby the torque should be under the motor capability to keep the motor turn at synchronous speed. What happens when the load change? So to find out, we take a look at this phasor diagram and assume that operate at leading power factor, and IA leads phase voltage, and at leading power factor generated voltage is lower than the phase voltage. This is motor because it's motor. So before the load increase, the internal generated voltage EA is depend only on the field current and the field current, how much the IF adjusted to the rotating poles in coils, and the speed of the machine. The speed will follow the rotating magnetic fields, the frequency of your line frequency, which is constant by the input of power supply, and the field current, which is set at constant. So EA is a little bit lower than V phase. What happens is that when we change the load, we increase the load, let's say, the rotor will start to slow down, and by right the rotor will operate at or rotate at synchronous speed and frequency of your line. When we put load, the rotor will slow down. Then the torque angle or the load angle, delta here, becomes larger, and the load angle between V phase to your EA, it becomes larger. So EA will swings down further and further, and it will decrease down. EA, instead of EA1, it will reduce to EA2, 3 or 4. And the induced torque increase, and the induced torque will increase. When we have more slip, the induced torque will increase. The increase in induced torque will speeds the rotor back up, and we have increased torque, the rotor speed will then increase, and torque increase, the rotor speed increase. Then the magnitude of JXIA has to increase, and the line here has increased to reach the tip of EA to V phase, and from EA here to V phase. Therefore, the armature current I also increase, as well as the power increase, and IA also will increase. Instead of IA1 here, the magnitude will increase, and IA2, 3, 4 like this. So, as well as the power, P1, P2 here will increase. The further it goes down, the higher the power. And the power factor change also will increase due to the changing of power factor angle here, and the changing of IA versus V phase, which is power factor. So it will change when we top up the load to the shaft. So in summary, we shall see the behavior or understand further from the exercise that we will discuss soon. So in summary, in terms of synchronous motor, to summarize, in terms of synchronous motor, the main feature of the synchronous motor is that the motor are actually not self-starting, and so it requires external means of rotating to rotate the shaft first to bring them to the synchronous speed before they lock or synchronize with the rotating magnetic fields. So the speed of operation in synchronism with the supply frequency, and also for constant supply frequency, they behave as constant speed motor. And so once it's locked to the frequency or the speed rotation as per supply frequency, so the speed will be constant at any kind of load. You put load, more load, unless you increase the load, exceed the load or the torque, and the maximum torque of the motor still will operate. And if not, once increase or exceed, so it will lock out. And so means that at zero load, and it's different with the synchronous motor, we put less load, the speed of for induction motor, less load, the speed will near the synchronous speed. We put more load, the speed will reduce a bit, and maybe down to 5% or up to 10% of reduction in kind of speed. But for synchronous motor, you put in zero load, minimum load, medium load, or maximum load, the speed will just as your supply frequency speed. And so at any respective load condition, the speed will be at synchronous. So this motor also has a unique characteristic of operating under any electrical power factor, and so it can be used as electrical power factor improvement. So it means that for the motor, you can operate as a lagging power factor or leading power factor to compensate and the load or the lines condition, and so it can be as a power factor condenser. So actually synchronous machine, it can operate both as a motor or generator. In some cases, such as pump storage, and they also operate as both motor and generator. And you can see in the pump storage, you want to you put in voltage, so it will absorb the water from the below to the upper reservoir. Once the reservoir is full, it can operate as a generator. You put in water throughout the shaft or the turbine will turn your shaft and turn your poles, so it operate at or behave like a generator only. So during motoring, the EA for sure will lack V phase, and we put V phase, we produce EA, and so the speed of rotor will lack speed of synchronous. Power flow is electrical to mechanical. This is motoring lah. We put electrical source, we produce mechanical turning shaft and force. As a generator, EA leads V phase, and we turn the shaft, produce internal generated voltage, and after you minus the resistance of your series coils, resistance, impedance, so you produce V phase. So for sure, EA is bigger than V phase lah. Rotating speed will lead your synchronous speed, and then power factor, power flow is from mechanical to electrical. This is for generating. So the speed torque curve becomes a straight line at 100% synchronous speed, and from load of 0 up to 100%, maybe you can increase up to 150% load torque. So you shall have a 100% of speed, and 100% of speed means that the speed will be constant. The motor maintain constant speed from no load up to maybe 150% of the full load torque. And so the synchronous motor runs only at synchronous speed, steady state, which is related to the supply frequency. If the mechanical load increase or decrease, and increase or decrease, you add up or you reduce, the motor will momentarily, and will be a little bit for the short time decrease, then will be readjusted and by the load torque angle with some oscillation. So then it will come back to the synchronous speed value. It will face, or it will feel some readjustment of the load or torque angle. Then you come to the synchronous speed again. So we shall go to the example in the next slide, and this is all the slides explanation on the motor and generator. So good luck for your exam later on. So the exam has changed already to the test 3. We cover 2 questions. One is for generator, another one is for motor. And so you are lucky because you don't have to study anymore on the DC machines and induction machines. You're just going to focus only on synchronous motor and generator. So the exercise will be discussed. I will upload on the coming slide. Okay, thank you very much. And very sorry and apologize from me for the lack or the unexpected and lecture from me and my team. Okay, good luck for your future. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.